about sense amplifier today. Okay. So why memories? Like we talked about the entire library, we talked about some arithmetic circuits, then why memories? What is so important about memories that we're talking about it in DVD course also?
So memories are the minimalistic storage elements which provides high density. So if we consider a case of a register or a latch or a flip-flop, then those involve large number of transistors. Even though they provide the storage functionality, they don't provide high package density. So we need to specifically look into memories.
Thank you, Ranjit. So you already made my task a little easier in the sense that what we are saying is that memories are high density storage elements, and they are so important that today they cover in advanced SoCs they cover up to 70 to 80% of chip area. So come to think of it, all that you've discussed in this course about libraries and everything, that is not even 20% of total chip area. Do you see that? And since memories cover that huge area or have such a huge footprint on a chip, we talk about memories in this course also. And that is also the reason why we have a separate course altogether on memories that will be running in the next semester. So why is it that memories consume so much of area, or why so much of area is given to memories? See, in a typical computer architecture, you will see that memories are there at various levels. There are register files, which could be shift registers, but which could also be small memories. There are caches of different level of hierarchy. First level cache, which is integrated inside the processor, it operates at the same speed as the processor. It has to operate it would possibly access every cycle. And if you've done the course on computer architecture, you also know that there is an instruction cache, there is a data cache, and there could be the concept of a unified cache also. So there are these caches, level 1 cache, level 2 cache, level 3 cache, and all that. So all this is on chip. And then outside the chip also, then you have main memory, which would typically be DRAM. We will cover about DRAM also in the memory design course. And beyond the DRAM, there will be non-volatile storage, the pen drives that you have where you would store your data. So do you realize that memories are kind of pervasive? As we move away from the processor, they're also becoming slower. So while register files operate at the data path speed, are really, really very, very fast, level 1 caches operate at processor speed. The second level caches may actually take multiple processor cycles. Third level cache may take still longer. And as you go to main memory, which is off chip, the time duration or the time of access increases multi-fold. Okay, so it would take hundreds of cycles to access a DRAM from a chip. So how you size these memories and how you organize this architecture is critical. And you look into quite a bit of it, I hope, in detail in the computer architecture course. How many of you have done the CA course? And have you covered these different hierarchy architectures, different hierarchies in memory architecture? So you're raising hands to tell me that you've done the course and you understand this, or you're raising hands to ask questions. So please ask. Ranjit?
No, sir, it was just to indicate.
Okay. Akash? That was also to indicate.
Yes, so, that was same.
Okay. Just 2 of you have done CA course, others have not done computer architecture course? I'm very surprised. Okay, so the chat window says +1. Okay, I get it. So many of you have done the CA course and you do understand that memory hierarchy is critical to manage, is important to manage. In MDT course, we will spend just about a lecture or 2 on memory hierarchy and how to size this up, because we have already covered it in CA. But we will actually spend more time on how to design the level 1 cache or level 2 cache, or the DRAM, so that you get the you achieve the desired objective, whether it is high density or high speed or low power, whatever it is. So Ranjit already mentioned that the standard, the latches and the flip-flops, they take much more area than a standard 60 memory cell. So we will come to just that. But before that, when we talk about memories, we also need to realize that whether it is register files or L1, L2 caches or L3 caches, there are different kinds of memories that come into picture. One set of memories is random access, which are static RAMs and DRAMs. But then on any chip, you would also have stuff like FIFOs. Have you heard about first in, first out FIFOs, which are used to implement queues? You also have last in, first outs, which are used to implement stacks. So when you do programming, you must have definitely, in data structure courses, you must know about stacks. So there are memories which would be used to implement stacks. Then there are shift registers, which you already know. And then there are content addressable memories. Do you know what is a CAM? Have you ever heard about it earlier?
No, sir.
Yes, sir.
Okay. Okay. Who has?
Sir, I have.
Okay. Can you tell us about it? What is a
Sir,
CAM?
it is yes, sir. So it is a type of associated memory that is used for high-speed searching applications. It basically finds the data and returns the address of matching data.
Great. So see, typically when you talk of a memory, you would typically give an address location, and you would want to find out what is written on that particular address. A CAM is something different. CAM does not know what the address is. CAM knows what the content is. So you search for the content, and that leads you to the address. And then from that address, you may do further operations. Now, where is it needed? Consider the case of a network router, a network switch. You know that you want to route some packet of data to Google's US office. So you want you know that the destination is US. But in a particular routing switch, all that you can tell is that, okay, out of these 4 switches, which one would take me closer to the US destination, to the US server? So you search for US in the contents, and whatever programming has been done at the router level, it will tell you, oh, go to port number 25. It will route your packet to port number 25. Now you switch the router off, you turn it on again. Next time round, it may route you to port number 29, port number 2, whatever has been configured. So depending on data, you will get a different address to go to send your packet to. That is what is content addressable memory. This is also very widely, or content addressable memories are tightly coupled to processors, so that when a particular instruction is given, the follow-up instructions are brought in quickly based on the content, by doing a quick content search as to which location is this particular instruction stored, and then I pull out remaining instructions from that region quickly. So CAMs are specific memories, and we will not really talk about them much in the course, but just for the sake of completeness, CAMs are also non-random access read-write memories. Now, while these are read-write memories and these are all volatile, like volatile means that when you switch off the power, the contents will get erased. So when you power up the circuit again, you will need to write inside the memory all over again. But you don't want, or you also need memories which would not erase all the data, is it not? That is where we have NV read-write memories, that is non-volatile read-write memories. These include electrically programmable ROMs, electrically erasable programmable ROMs, and flash memories. So what is the use of these flash and EEPROMs and EEPROMs? Anyone?
So these memories, firstly, they provide the non-volatility, and the second thing is that these can facilitate the not a large number of writes, so they can be erased and written.
Yeah. So EEPROMs over here cannot be erased, but EEPROMs can be erased. So EEPROMs are electrically programmable ROMs. So what you do here is you kind of blow away the fuses. Once the fuse is blown, now you cannot rebuild it again. So EEPROMs, where would they be used? Can you think of a use case?
Boot sequence.
Yes, boot sequence. Or, for example, there is a standard set-top box chip which you also sell to Airtel and you sell to Bharti and you sell to Tata Sky and you sell to Dish TV and everyone. Now, Dish TV wants to program such that people cannot use their set-top box or their Dish TV, their box with, let's say, Tata Sky. So they will use the EEPROM there to program the memory and prevent access from any other provider to this particular box. EEPROMs would also allow erase. They could be, for example, for boot code, where we say that, okay, it may happen that I want to give a firmware update 1 year down the line. So I should have the flexibility to erase also. So EEPROMs would be used there. And then flash. Flash, all of you know. Where would you use flash? Where would you use flash?
Sir, our memory cards and everything has flash
Yeah,
memory.
your cell phone has a flash. Everything, all the solid state storage that we talk about is with flash. So then there are ROMs. ROMs are read-only memories. You cannot write into them. Where do you use a ROM?
Again, sir, booting
PC.
data and all those.
In a boot sequence. In those parts where you are just stored which address location, for example, you would go to get the first output or stuff like that. So boot sequence would typically be stored in ROMs. This you cannot change. Once it is programmed, you cannot change it.
All the code memory will be of type ROM.
Yes. So this is the wide range of memories that exist. So we will talk about, as I mentioned, SRAMs, we will talk about DRAMs, LIFOs, CFOs, shift registers, and CAMs we will not talk about as much. But we will talk about EEPROMs, EEPROMs, flash, and then ROMs when we will do the MDT course there. Okay. Now, when we talk about these different on-chip memories and off-chip memories, so on-chip memories are typically SRAMs. Whether we're talking of L1 cache, L2 cache, L3 cache, when it is on-chip, it is typically SRAMs. They are very fast, but they're not as dense. We talk about 6 transistor SRAMs. You've heard about 60 SRAM cells? 60 SRAM cells? No one?
Yes, sir. So it has 2 transistors to control the bit lines and the 2 back-to-back coupled inverters.
Yeah. So 60 transistor cells. So we are talking about 6 transistors to save 1 bit of data. When we talk about DRAMs, DRAMs are 1 transistor and 1 capacitor. And flash is actually effectively less than 1 transistor per bit of data. On every transistor, you could actually be storing 2 bits or even 3 bits of data. And that is where it is much more dense. Endurance means the number of times you can read-write into that particular memory. So in a SRAM, it is 6 transistors, fully static CMOS logic, regular voltage operation. Endurance is maximum, very high level of endurance. DRAMs, again, very high level of endurance. Even though we have a capacitor which could leak a little, but even then the endurance is very high. But flash, we actually, when we will do the course, we will see that in flash we actually use very high voltages, and therefore endurance goes bad. We cannot really do as many number of reads and writes as you can do in a SRAM. So there are various figures of merit, speed, density, endurance, power, refresh. So what does refresh mean? What does refresh mean? Anyone?
Restoring the data that was stored on the cell.
Yes, refresh means that if you do not restore the data on a regular basis, then what happens? If you do not restore the data on a regular basis, you may actually end up losing data. You may actually end up losing information. So you have to refresh. And DRAMs, because they store data on a capacitor, it's a floating capacitor, that can leak. This charge can leak. Therefore, you need to refresh the DRAM, the contents of a DRAM. Okay. Retention, we already talked about. As you switch off, the power would go off and the contents would be erased. And then mechanism is bistable latch or a capacitor, or in a flash with using a mechanism like FN tunneling or hot carrier injection to be able to do read and write operation. Okay. Faisal, you have a question?
So first thing is, when we were talking about flash, you were saying on one transistor we will store 2 to 3 bits. So how is that possible? Like a transistor pe?
Magic. So we have a floating gate there. We use till now we've just looked at a gate, oxide, and then the substrate.
Yes,
In
sir.
flash, we use special kind of devices where you have gate 1, you have silicon dioxide, you have gate 2, you have silicon dioxide, and then you have the substrate.
Is it like the floating gate or something? No, sorry. FG MOS, floating gate MOS.
Yeah, so you have a floating gate there in which you can trap charges.
Okay. Okay. Yes, sir.
So when you trap charges, the VT would change, and then you will be able to say that what is the
Yes.
kind of data stored there.
Okay. And so one more thing, can you please reiterate why do we need to refresh?
Because in DRAMs, you're storing data on a capacitor. It's like a dynamic gate. So why did you need to use a keeper there? Because that data would leak. Some charge sharing can happen, something can happen, some mishap can happen due to which that data can be lost. So you put a keeper in a dynamic gate, is it not?
Yes, sir. Yes, sir.
Now for a DRAM, if you start to put keepers in every cell, then you will become a 2T 1C cell. Area would double. We don't want that.
Yes, sir.
Therefore, we say, okay, we will keep 1T and 1C, but every now and then we will refresh the data. We will recharge, we will put the charge on the capacitor again.
Yes, sir. Okay. Understood. Thank you, sir.
Okay. Yeah. So that's a quick overview of different kinds of memories that we have. But whatever be the kind of memory, you will see that we can still cover them in one course because they are organized in a very standard way. What you have is a structured array of storage elements which are accessed. If let us say we are storing one word in this particular row, then we have a decoder which would select a particular word, and we have IOs which would give out the output. So by putting them in a structured array, we are able to actually make the array much, much denser, and also use lesser periphery circuits or lesser additional circuits than what you would use in a latch. So the structure of all the memories, whether we are calling it DRAM or SRAM or flash, would typically have a core array, would have decoder region, and would have IO region. We'll look into it in a little more detail a little later. But let us look at the benefit of having a structured core array.
I have a doubt, sir.
Yes, please.
Sir, always when it comes to the memory structure, will we just have an M-cross structure, sir, or do we have any other structures?
Oh, so there will be many structures. This is the most rudimentary basic structure that I'm introducing you to over here in this class. When we go to memory design course, you will see there are hierarchical architectures, there are other structures also. But still, this basic tenet that there is a cluster of storage elements which are closely coupled, not only through word line, but also through bit lines, that tenet remains constant. Okay. That there is some decoding architecture there, that tenet remains constant. That there are IOs which would have circuits to buffer the output, that tenet remains constant. That there is some brain, some control region somewhere, that tenet remains constant. So since these tenets remain constant, we start with a very basic architecture.
Okay, sir.
We can go into much more complex architectures, and we do go in the course itself. We do go.
Okay. Okay, sir.
Okay. Yeah. So if we look at this basic architecture only, where we have a control, decoders, array, and IOs, this control region is the brain of the memory. Okay. This would have circuits which would tell whether it is a read operation. So if it is a read operation, it will tell, okay, activate this set of signals. If it is a write operation, it will say activate the other set of signals. If it is a dummy operation, it would say, okay, save power, and all that. So this control region, you may say, is the brain of the memory. It controls the state machine. So in a memory, you could do multiple operations. Say in a latch or in a flop, you would just trigger the clock and the latch will be written into, and it will also output in the same cycle or whatever will happen. In a memory, by the virtue of consolidating a big array and everything, you separate the read and write operations across cycles. You say, okay, when I want to write, I will use one particular set of inputs. When I want to read, I will use another set of inputs and outputs. Okay, so there are different states that the memory can be in, and that is controlled in this control region. The control region has what we call as a clock generator and what we call as some address pre-decoding also in it. So when the addresses come, they are pre-decoded, and when the clock comes, an internal clock is generated. These pre-decoded addresses and the internal clock go to what is called as a post decoder. And this is generic. Again, across all memories, you will have this. Now, how many post decoders you have, what is the architecture, that may change, but you will still always have a post decoder. Okay. The post decoder would generate what we call as a word line. It will select a particular row. When a particular row is selected, the memory cells, the storage elements stored in that particular row, will discharge bit lines. Now, in this case, because I'm starting to talk about SRAMs, I'm showing a differential, a pair of bit lines, bit line and bit line bar. But in SRAMs also, you have single-ended, just one bit line per memory cell. And then when we talk about ROMs and when we talk about DRAMs and when we talk about flash memories, you would typically have only one bit line per memory cell. Why don't we have 2 bit lines in those ROMs and DRAMs? We've done layouts now. If I have to route 2 metals versus 1 metal, what is denser?
One metal is
And
dense,
one
so I
metal.
won't need space.
Yeah. So we want to keep as dense. We talk about ROMs to be very, very dense, DRAMs to be very, very dense, flash to be very, very dense. So for that purpose, we do not go for differential bit lines there. But when you select a memory cell, some bit line would discharge. And that discharge you will measure, you will estimate, and you will observe at what is called as a sense amplifier. Okay, so once the discharge has happened, you trigger the sense amplifier and you output you output the differential, or you enhance the differential, and you give a 0-1 output on the Q pin. Okay, so this is a typical read operation as it would happen inside a memory. When you talk about a write operation, you will still have word line selection the way we talked about, but you will also have another clock going from here, and you will have what you call as a write driver. So data will come from outside, and write driver will discharge one of the bit lines, either bit line or bit line bar, and that would be written into the memory cell there. Okay. Any questions here? Okay. So again, this is just to give you an intuitive feel of how different components, or how a signal flow, a clock flows inside the memory to accomplish a complete read and write operation. Okay. So this is a D latch. How many transistors can you count in it quickly?
14 transistors.
14 transistors. But do you notice that of these 14 transistors, there are a few transistors which are not really needed, or there are a few transistors which could actually be shared across memory cells? For example, consider the case where word line is not selected, or where the clock is not coming. So clock is 0 means both these PMOSes are on. Am I right? If these PMOSes are on, then I'm effectively having VDD directly over here. So in a way, these 4 PMOSes are not required 99% of time, because for a memory, the clock would come rarely. So you have 1000 words in a memory. Even if you access memory in every cycle, any particular word will be accessed only 1 in 1000 times. So more than 99% of times, this PMOS is not getting selected. These PMOSes are simply waste. VDD is already coming here. Are you able to see this? Friends, if you don't ask questions, the questions will simply linger on in your minds. Is this clear? Are you able to understand why I said that 99% of times the CK is 0 for a particular memory storage element? Is that part clear?
Yes, sir, that is
No,
clear.
sir.
Sir,
It
I
is
have a
not
doubt
clear.
that
Sorry, Vaishnav. Yeah.
Yeah, Akash, please.
no. Sir, I just want to know that you said in 99% of the cases we don't need these PMOSes. But sir, as you said, the 1% case, what will be the alternative way to implement that 1% case?
Yeah. So you tell me, if I do not use a full CMOS circuit, what do? We have already done some such circuits where we were not using full CMOS. So what were the constraints that were coming on our way?
So like we can use a domino logic or something that.
Okay. We do not want to make a DRAM. We want to use static logic only. So what was the static method in which we were not using the PMOS stack, or not using the PMOSes, as many PMOSes?
We were using the pseudo
Pseudo-NMOS. And what was the
Yeah.
challenge of designing pseudo-NMOS? Sizing. So as soon as I remove these 4 PMOSes, I have a pseudo-NMOS circuit then. What this means is that I have to size my devices very carefully. Are you able to see this?
Yes, sir.
So these 4 PMOSes are not required for 99.9% of time. Therefore, you say I remove them. But for that 0.1%, you still don't want to fail. And for that, you have to do the sizing. Okay.
Okay, sir.
So Vaishnav, what did you not understand? You said nahi aaya samajh mein. What was
It
it that
was
you could
me.
not? No,
It was
Faisal,
me.
yes. Yeah.
सर 99% वाला कंसेप्ट नहीं, बाकी ये वाला तो क्लियर है कि
So
हाँ
let us
0.
say there are 1000 words in a memory.
Yes sir.
In any cycle, you will access one word.
Yes sir.
So the remaining 1000 words or 99 words, they are not
Okay,
being accessed.
99% of okay, मैं clock cycles में कंफ्यूज हो गया था. ठीक है, अब अभी क्लियर है.
Yeah. So for the 99% of cells, the clock is not coming, na?
Yes sir, yes sir, yes sir. Okay.
Hello. In
Understood.
reality, this is 99.99, something still higher.
Yes sir, yes sir.
But you can't let that 1% or 0.1% or 0.01% also fail. That
Yes,
is where
sir.
you need to be careful about the sizing. That is where sizing comes into picture.
Yes sir, understood.